Hello dear learners. In our today's class, we are going to continue with our lectures of conductance. And today we have to move on to the further part of our lecture. And today we have to talk about the variation of conductivity and molar conductivity with ionic dilution. See, first of all, we will understand that what do we mean by dilution. Suppose we have 1 centimeter cube of a particular, let's say this is a three-dimensional 1 centimeter cube volume, and here suppose we have n number of particles. Now suppose these are the solute particles. Upon the addition of solvent, now the solvent particles will also occupy this space, and because of which in the same area there will be now less number of solute particles available. So this time only, let's say, 3 solute particles are available. So here the number of solute particles decreased, and this is what we call as dilution. With this concept, there are two important and related terms. Suppose these solute particles were the ions. So these ions had the property to conduct the electricity. Now there are two important terms here. One of them is conductivity and one of them is molar conductivity, which are related to the property of ions to conduct electricity, and that we had discussed in our previous video. If the concentration of the particular solute molecules or particular ions are decreasing on dilution, that time the conductivity will also decrease, because less number of ions will be available in a particular volume to conduct the electricity. But at the same time, the molar conductivity of that particular electrolyte will increase. Why? Because in our last class we discussed that molar conductivity is nothing but conductivity multiplied by 1000 upon C. So here molar conductivity has inverse relation to the concentration. So if the concentration is decreasing upon dilution, the molar conductivity has to increase. So here there are certain important points which we need to know, which talk about the variation of conductivity and molar conductivity with the ionic dilution. So first point was this only, that if the concentration of the particular electrolyte in the solution is increasing, so that time the ions per unit volume available will be high, and in that condition the overall conductivity will increase. And if the concentration of the electrolyte decreases, that time the ions available per unit volume will also decrease and the overall conductivity will decrease. Now conductivity always varies with the concentration. This we have studied from here, and we can say that conductivity is somewhere proportional to the concentration. But this conductivity with the increase in concentration may vary for strong electrolytes and for the weak electrolytes. In strong electrolytes, let us take the examples of HCl, NaCl and KCl. In the weak electrolytes, let us take the example of ammonium hydroxide and acetic acid. So right now I told you that if we are increasing the concentration, the conductivity also has to increase. But will this conductivity increase proportionally, or will this conductivity increase gradually? That is what we need to understand. So in the case of strong electrolytes, if you are increasing the concentration, that time the number of free ions per unit volume will increase. Why? Because you are increasing the concentration of AB, and this AB being a strong electrolyte will directly and immediately dissociate into A plus and B minus. So more the AB, more will be the A plus and B minus, and because of this more will be the conductivity. So I can say that the conductivity will increase rapidly. As we are increasing the concentration, the conductivity increases rapidly. But here there are certain different things in the weak electrolytes. Suppose you are increase in the concentration of weak electrolyte. Now this weak electrolyte may dissociate into A plus and B minus and may again become the weak electrolyte. So here the conditions are different. Overall what I can say is that if I am even increasing the concentration of weak electrolyte, the conductivity will increase, but it will increase gradually. Means it will not increase as rapidly as it was increasing in the strong electrolyte condition. So this is first important point, that if we are increasing the concentration of strong electrolyte, the conductivity will increase rapidly, and if we are increasing the concentration of weak electrolyte, the conductivity will increase but gradually. Let's come to the second important point. The second important point now talks about the molar conductivity. Let's see the effect of molar conductivity, that what will be the effect of molar conductivity here. Now I told you that molar conductivity and conductivity behave opposite to each other. So for the strong electrolytes and the weak electrolytes, if we are increasing the concentration, the molar conductivity has to decrease. And if we are increasing the dilution, the molar conductivity will increase. So one thing is very common in both strong electrolytes and weak electrolytes, that this molar conductivity increases when the concentration will decrease and when the dilution will increase. So upon the increase of dilution, the molar conductivity of strong electrolyte or weak electrolyte will increase. Let's first take the case of strong electrolyte. Let's say we have some strong electrolyte, taking the example of NaCl itself, or taking the example of HCl. So if we are increasing the dilution, they will be dissociated, right? The strong electrolyte will directly dissociate into A plus and B minus. And if more the dilution we are doing, so more will be the dissociation. But here there is a twist. As soon as you are adding the strong electrolyte, it is not reversible to this reaction. If the strong electrolyte is added in the solution, it will obviously dissociate. So even if you are increasing the dilution, here only the molar conductivity will depend upon this dilution factor, not the original electrolyte. Because we know that if the ions will be having more free space, so they will be more easily able to conduct the electricity through the solution. So that time the molar conductivity increases. So here the molar conductivity depends only upon the dilution factor and not on the electrolyte, because the electrolyte is itself dissociated from the very beginning. So here it is almost a linear graph, which is somewhat like this. Let's take the example of this. Suppose this is my y-axis and this is my x-axis, and here if I am trying to plot it, the graph for the molar conductivity and for the root of concentration, so I will get this kind of graph. This is almost a linear graph, or I can draw it very linearly, like this type of graph I will get. Now what does this type of graph signify? That as the concentration is decreasing and the dilution is increasing, the molar conductivity is increasing, and this is all occurring linearly. So this is my condition of strong electrolyte. Now we are taking the condition of the second case, where we talk about the weak electrolyte. In the case of weak electrolyte, for example, let's take acetic acid. Now this acetic acid which we are taking here will dissociate reversibly into CH3COO minus and H plus. Now what is the meaning of reversible here? Reversible means if the dilution is increasing, this equilibrium will shift to right hand side, and if the dilution decreases, this equilibrium means if the concentration of the electrolyte is increasing, that time the dissociation will not occur and the equilibrium will shift to left hand side. And this is in confirmation with Le-Chatelier's principle. So now suppose if you are increasing the dilution. So suppose the dilution is increasing. In that condition, according to Le-Chatelier's principle, for this equilibrium, it will also shift to the right direction. So the dilution will also increase and the dissociation of that electrolyte will also increase. So what I mean to say is that here the molar conductivity will depend upon two factors, one of them being dilution and one of them being dissociation. That as you are increasing the dilution, that is also one of the reasons for increase of molar conductivity, but in addition to that, the dissociation of electrolyte will also occur, and as a result both of the factors will together work, and here the molar conductivity will increase rapidly after a certain point of time. But in the case of strong electrolyte, it was always a linear plot. So if I try to draw the diagram here again, suppose this being my y-axis and this being my x-axis. The y-axis is showing the molar conductivity and the x-axis is showing root of concentration. So here I will get this kind of graph. So this is a rapid increase. Here you can see there is a rapid increase in the molar conductivity after a certain point of time. And for this there are certain concepts also which explain this, being them the Arrhenius concept and the other concepts also which we are going to talk about very soon. So first of all, you should now know that molar conductivity will increase if the dilution is going to increase, and it will behave differently in the case of strong electrolyte wherein the molar conductivity was increasing linearly. But in the case of weak electrolyte, the molar conductivity was not increasing linearly, rather it was initially very slow, but after a point of time it increased very rapidly. So that is what you need to know about the molar conductivity. Now, why this type of behavior? Like for strong electrolytes versus weak electrolytes, we saw a difference in behavior. When we were increasing the dilution, the strong electrolytes show the linear increase in molar conductivity, but the weak electrolytes were showing the rapid increase in the molar conductivity. So why is it happening? So that was explained by certain scientists, and we have to know and we have to learn their concepts. So now we are going to talk about the first concept, that is Arrhenius theory. Now this Arrhenius theory works for the weak electrolytes. So according to the Arrhenius theory of electrolytic dissociation, there is always an equilibrium. So if I say this is my electrolyte AB, so it will always be in an equilibrium with its ions or with its dissociated form. And this is my weak electrolyte. So I will write here it is applicable to weak electrolyte mainly. So now, depending upon that what the conditions we are providing, and that I have already explained you, suppose we are increasing the concentration and we are decreasing the dilution, this equilibrium has the tendency to shift to the left hand side. Means the concentration of AB will now increase. And if we are decreasing the concentration and we are increasing the dilution, the equilibrium will have the tendency to move to the right hand side, and that is the concentration of A plus and the concentration of B minus ions will increase. And this is in the confirmation with Le-Chatelier's principles. So from here we can derive one important concept, that is degree of dissociation. This is one of the important terms. It talks about that how much the ability of electrolyte to dissociate into its constituent ions. The degree of dissociation is also represented by alpha, and it is nothing but lambda m, that is molar conductivity at a particular concentration, upon lambda m infinite, that is molar conductivity at the infinite dilution. And always remember that this molar conductivity at infinite dilution is also known as limiting molar conductivity, and we are going to talk about this concept further also in our upcoming videos. But please know that the molar conductivity at infinite dilution, which is also represented by these two terms, it is also referred to as limiting molar conductivity. Okay. Now it was further quantitatively expressed by Ostwald in 1888. So now we have to talk about the Ostwald's extension and what did he do. So basically he again considered the similar kind of equilibrium here. Suppose we consider this equilibrium between the weak electrolyte and its constituent ions. Now this equilibrium is always there. Now if we want to calculate the equilibrium constant for this reaction, the equilibrium constant will be equal to the concentration of products, that is A plus and B minus upon the activity of the reactants. Now suppose at time t equal to 0, if I consider at the 0 time, that time this will have its full concentration and it will not be dissociated, so the concentration of A plus and B minus will be 0 and 0. But after a certain period of time, suppose at time t, some part of it will dissociate, right? So it will be equal to C minus C alpha. C alpha of it will be removed and it will be forming this one. This is like C alpha amount of A plus and C alpha amount of B minus, right? So in this condition, our K equilibrium will become what? Our K equilibrium will become C alpha multiplied by C alpha upon C minus C alpha. We can also write it as C alpha or like C square alpha square upon C 1 minus alpha. And if I cut this C with this C, so it will turn out to be C alpha square upon 1 minus alpha. Now this alpha is very small. It is very small for weak electrolytes. See, I will tell you how. If you know about the concept that we were talking about right now only, that is the degree of dissociation is lambda m upon lambda m naught. For weak electrolytes, this is very high, and because of it being high in magnitude, this will be very less. So this will be very less, approximately 0.01 or somewhat like that. So we can even ignore this alpha term. So that time the K equilibrium turns out to be C alpha square, and from here we derive another important formula for this degree of dissociation, and it is equals to K upon C and its root. So that is what we call as Ostwald's dilution law. So I will write it here. It is also referred to as Ostwald's dilution law. So this is the Arrhenius concept and the Ostwald concepts which are applicable to weak electrolytes only. Now if we talk about the concept of strong electrolytes, let us see what is it. See, strong electrolytes, they are dissociated completely. They are dissociated completely means this AB will turn into A plus and B minus completely. So their degree of dissociation is 1, if you can see from here, because they are completely dissociated. So even if we try to apply this formula C alpha square upon 1 minus alpha, this is 1, so it comes out to be 0. So what I mean to say is that for these strong electrolytes, the concept of Ostwald dilution law and the concept of Arrhenius theory will not be applicable, because here the degree of dissociation comes out to be 1. So for the strong electrolytes, why they are showing the linear behavior? See, unlike these weak electrolytes which we were showing the rapid behavior, these strong electrolytes are showing only a linear behavior. Why not rapid? What is resisting them from showing this kind of behavior? That is what was explained and put forward by another important scientist, and the scientists were Deby and Huckel. So Deby-Huckel theory of ionic atmosphere. Now this is a very important term and you should know it. Means basically what we are trying to understand here is that unlike the weak electrolytes which were also showing the rapid increase in the molar conductivity with decrease in dilution, why don't these strong electrolytes also show this rapid increase? Why is there a linear graph? That is what was explained by Deby-Huckel theory. So we know, and Deby-Huckel they propose this concept that this strong electrolyte will be from very initial. Okay. Will be dissociated into A plus and B minus. In that condition, please understand this, if they are always dissociated. So what happens is there is generally a central ion, and this central ion inside the solution, because now they are in the ionic form only, there is no electrolyte form. So this ion will actually be surrounded by the oppositely charged ions. Now this is the oppositely charged ions which are surrounding this, and vice versa to this, there is suppose this central ion, so it will be surrounded by these oppositely charged ions, and these oppositely charged ions are only referred to as the ionic cloud or the ionic atmosphere, which is surrounding the central ion. So now what happens is that suppose if there is no uh, electric field applied in the solution, suppose this is our container and there are no cathode and anode, only what we have is the electrolyte. So in that condition, this central ion will be surrounded by its ionic atmosphere, and this central ion will also be surrounded by its ionic atmosphere. This ionic atmosphere will be quite symmetrical, and this will also be quite stabilized, as it is not in any disturbance. So that time it is normal. But now what we are trying to do is we are trying to calculate the molar conductivity, and molar conductivity, which we also call as the ability to conduct the electricity through it, right? So ability to conduct electricity means now we have to pass the electricity and we have to check whether they are able to conduct the electricity through them or not. So now what we are going to do is now we are going to join the electrodes here. Suppose this being my cathode and this being my anode, or let's say vice versa, this is being my anode and this is being my cathode. Okay, and now I've connected this also to a battery, suppose like this. Now what happens is we are trying to apply the electric field, and now the electric field will move obviously, so it will start. Suppose it is moving this way. What happens? Are they able to conduct the electricity through them? Yes, they are able to conduct the electricity because these are the ions, and whenever they are under the presence of electric field, they will conduct electricity. But why are they not conducting electricity very rapidly? Like in the case of weak electrolytes, even they have been diluted, then why are not they doing it? Because when this central ion, suppose this is our central ion, when it tends to move forward, suppose it is being my positively charged cation and it is trying to move towards the cathode. So what happens is there is this ionic cloud, and this ionic cloud distorts in this way. We already know that this ionic cloud is negatively charged, so it has to move towards the anode. So it has to move this way, but this has to move this way. So what is happening is there is a resistance generated, and this resistance is dragging this positive ion to move towards the cathode. So here the speed or the mobility of this positive ion will become less, and in that condition this will not be able to reach quickly to the cathode. And here, because of this resistance, the overall conductivity will be there, but it will be slower as compared to the weak electrolytes. So this is one of the effects which is called as asymmetric effect. Okay, this is your asymmetric effect. The another one being the solvation effect. The solvation effect simply says that now you only see yourself whenever there is an electrolyte or ion which is dissolved in the solvent. So what happens is that particular solute is surrounded by the solvent molecules, so that this particular solute molecule can dissolve. For dissolving of this solute molecule, the solvent molecules will surround the solute molecule. Now this solute molecule is loaded. It has become heavy. So even if it has to move, there will be, because of the solvation which is done by the H plus or let's say H3O plus ions, which were also present there. See, the solvent is water. So if we are using water here, the H3O plus ions will be there. So these solvent molecules, because of the phenomenon of solvation, will surround this cation, and hence it will be not able to move towards cathode rapidly. So in that condition also, the overall molar conductivity will increase, but it will not increase very gradually. Now there are other important effects which we need to know. One of them being vane effect. What is the meaning of vane effect? Vane effect says that if you are applying a very high electric field, suppose greater than 10 to the power 5 volt per centimeter. In that condition, if this much high amount of electric field is applied, all the effects are being removed. So basically what happens is the asymmetric effect which was earlier existing, it is removed on the application of this high amount of electric field. So in that condition, now even if there was an ionic cloud, that ionic cloud has been removed because of this very high electric field, and the ions will now move rapidly. So what I mean to say is that if in a strong electrolyte you are trying to apply a very high amount of electric field, then the asymmetric effect will become negligible and the ions will move with a high speed towards their respective electrodes, and hence the overall molar conductivity will also increase rapidly. So if you have to increase the molar conductivity very rapidly in such strong electrolytes, then you have to apply a very high amount of electric field. The second important effect is Deby Falkenhagen Falkenhagen effect. This effect simply says that if you are using a high frequency AC current, in that condition, because of the high frequency, the asymmetric effect will also be removed, the electrophoretic effect will also be removed, and even if there is a solvation effect, that will also be very much removed or minimized. In that condition also, the ions will move with a very high speed towards their respective electrodes, and overall molar conductivity will increase very rapidly. This is your Deby Falkenhagen effect. In our next class, we are going to talk about the Colruyt law of independent migration of ions.